All right, let's start our lecture for today. So previously, we have we've a look at how do we calculate the effective length of column. So now we want to calculate another term that is called the limiting slenderness ratio. Okay. So EC2 close 5.8.3.1 places an upper limit to the slenderness ratio of a single column. So the second order effects may be ignored. Okay. So if your lambda limit is, if your lambda of your column is more than lambda limit, then you need to consider second order effects. So meaning that your column is slender, right? If your lambda of the column is smaller than lambda limit, then it will be a short column. So short column, you do not need to include the second order effects, right? So lambda limit is given as 20 times factor A times factor B times factor C over the square root of factor N, right? So let's look at one by one. What is factor A? So A is related to effective creep ratio given by this expression here. Okay. So if you don't know what is the effective creep ratio, then you can leave A as 0.7, right? And then factor B is dependent of the reinforcement, right? So therefore you see that this is the area of the reinforcement as times the design stress or U stress of the steel over the area of the concrete, cross-sectional area of your column, okay, and then times the design concrete strength, FCD, okay, and then factor C, okay, is related to the what I call the moment or first order moment that is acting on your column. So you have n number one. Normally n number one we put as the lower end of the column, and the M02 will be the first order moment of the top end of the column normally. Okay. So normally the magnitude of moment M01, normally this is the larger magnitude. Okay, and then this is the smaller magnitude of column. So one moment is at the upper end of the column, the other moment is at the lower end of the column, right? So if you don't know what is the column moment, okay, then you can put C as 0.7 also if the ratio of the larger moment in the column over the smaller moment in the column is not known, right? Okay. Oh, sorry, the other way around. Magnitude of moment at N2 normally is the larger moment, okay? And the M1 normally is the smaller moment, okay? So it's a reverse of that, what I have explained just now. Sorry about that, I made the mistakes here. So normally the M02 refer to the larger moment magnitude, and then M01 refer to the smaller moment magnitude. So you have a column with two ends. Definitely there will be two moments, right? Take for example this column here. So you have the top end and the bottom end. Okay, so normally M01 refers to the smaller moment at the end with the moment M01, and then if the moment on top here is larger, then you call this M02, right, in terms of magnitude. Okay, so and then NED is the design ultimate axial load in the column. Okay, and the FYT is the design yield strength of the reinforcement. FCD is the design compressive strength of the concrete over here, as I explained just now. The AS is the total area of longitudinal reinforcement. Okay, so normally in design, we do not know how much steel that we have, right? So if you are checking a column, an existing column, then you know what is the area of steel that you put in the column. So you may calculate vector B based on the known reinforcement area, right? Okay, so the following conditions apply to the value of C, especially this C factor. So this one, depending on the direction of the moment. Okay, so if the M moments M01 and M02 give rise to tension on the same side of the column, so RM should be taken as positive, from which it follows that the uh, factor C is smaller than 1.7. Okay, so what it means here, M01 and M02 give rise to tension on the same side of the column. So meaning that if you have a column like this, okay, the top moment here will go in that direction, okay, and then the bottom moment here also go in this direction, okay. So the column will try to bend in this direction, right? Okay, so this is what we call as a single curvature also, okay, because there is only one notation of the curvature in this manner. So if your column bend this way, okay, so this side will be tension. The column here will be in tension on this side. Okay, let me draw the columns properly first. So if your column bends like this, okay, so this side will be in tension. This side will be in compression, right? So at the bottom end here also, tension is on this side, compression is on this side, right? So this is what it means by give rise to tension on the same side of the column, right? For the top and the bottom, they all have the same type of stress, because the column will bend this way. Okay, so this side will be compression, and this side will be tension, yeah? Right? And then if the column is in the state of double curvature, then Rm should be taken as negative, from which follows that C will be greater than 1.7. So if you have, let's say, a moment in the top end going this way, and then the moment at the bottom goes the other way. So in this case, your column will be bending like this. Okay, so there will be two curvature. That's why we call it double curvature, right? So if your column bends like that, right? If your column bends like this, I'm exaggerating the bending here, okay? So you have tension on this side, compression on this side, and then it becomes compression on this side, tension on this side for the column over here. Okay, so the tension here, okay, on the left-hand side, and then you have compression at the near the bottom of the column with compression. But on this side, you have compression on the top part of the column, and then tension is on the lower part of the column. So this is what we call as column bending in the state of double curvature. Then Rm should be taken as negative, from which follows that C is greater than 1.7, right? So meaning that one of these is taken as negative, the other one is taken as positive. So you have a negative Rm value. Okay, so if Rm is negative, then minus negative become plus. So this C will be greater than 1.7, right? If Rm is positive for the single curvature that I've shown you just now, then it will be 1.7 minus a positive value, right? So it becomes less than 1.7. So that's what it means by this one. C will be smaller than 1.7 if it's a single curvature. Okay, so C will be more than 1.7 if it's a double curvature, right? And then the third description is saying that for brace members in which the first order moment arise only from or predominantly due to imperfections or transverse loading. We will learn about imperfections later, yeah? Okay. And then here it says for brace members in which the first order moment arise only from or predominantly due to imperfections or transverse loading, then Rm should be taken as 1.0. Okay. So meaning that your C factor becomes 1.7 minus 1, so it will be 0.7, right? So for brace member in general, Rm should be taken as 1, so C is equal to 0.7 or so. All right. So in the actual slenderness ratio, if the actual slenderness ratio is less than the calculated value of lambda limit, then the column can be treated as short. As I mentioned just now, if the lambda of your column calculated is smaller than lambda limit, then the column is short. So if the lambda of your column is greater than lambda limit, then it becomes a slender column. So slender column, there will be second order effects arising from the deformation. So you will have the second order moments, right? So that's the difference between short columns. So short columns, you do not need to consider second order effect moments. But for slender column, you need to consider the second order effects column. So we'll learn all these design procedure in a short column and slender column. Okay, then you understand better what is the additional moment due to second order effects, right? So any questions so far? No question. Okay, then move on to the tutorial question, yeah? So here you have a problem saying that determine if the column in the brace frame, so brace frame meaning that you have brace columns. So we want to know whether it's short or slender. Okay. So the concrete strength is 25 Newton per square millimeter. Ultimate axial load is 1,280 kilonewton. And then the column will have the highest slenderness ratio for bending about about y-axis, where h equals to 300 mm, and also the end restraint as the stiffer 300 by 500 mm beams. So here you have different you have different beam size. So this beam depth is 700. Okay, the beam running into the page or out of the page is only 500 mm depth. Okay, and then this is the cross section of this beam here, and then this is the cross section of the column, right? So the column is 400 mm. 400 mm is in this direction, right? Okay, 400 mm is in that direction. And then in the direction into the page or out of the page, so meaning that on that side, on this side is only 300 mm, right? So from here, you see that the column y-axis is this, okay? Y-axis normally is the smaller, the weaker axis, right? And then z-axis is normally the stronger axis, because if you calculate izz, it will be larger than iyy. Yeah? Okay, so normally z is the stronger axis. So if you look at the pair of beams restraining z-axis moment, it will be this beam and this beam at the top, and then this beam and this beam at the bottom. Okay, so this beam will resist the bending or the restraining bending in the z-axis direction. Okay, so if the column is going to bend this way or this way, okay, so the beam restraining the bending will be these four beams. Okay, this beam, two beams on top, and then these two beams at the bottom. You will resist the bending with about z-axis of the column, right? So meaning that this beam and this beam, so this beam is this beam, and then this beam is this beam, right? And then for bending about y-axis, so bending about y-axis is restrained by this this beam here and this beam over here, right? So this beam, and this beam, okay, this beam is this beam here, okay, and then this beam here is this beam over here, okay, the one that is shaded. So for y-axis bending, it will be restrained by this beam and on top, and then this beam at the bottom. So the measurement of the beam restraining y-axis bending is 500. Okay, that's why you have a beam arrangement like this. You see that the beam, okay, the beam restraining the stronger axis zigzag is much stronger, which is 700 mm depth, right? And then those beam restraining y-axis bending, the depth is only 500 mm. So in this case, by inspection, okay, we know that the bending about y-axis will be more critical than the z-axis bending. Okay, so in this tutorial question, we only calculate the slenderness for only y-axis. Because if y-axis is you get a short column, then automatically the stronger axis, z-axis, the z-axis will have even a smaller lambda value. Okay, so I'll explain this later, yeah, when we look at the the examples, right? Okay, so this is how we are going to solve this equation, this problem here. All right. So the top of the y-axis, okay, for y-axis bending, it will be restrained by this 500 mm beam, and then the column is 300 mm, right? So let's look at the okay, so meaning that this one will be, this beam will be taken as the restraining beam, and then this beam will be taken as the restraining beam about y-axis bending, yeah, right? Okay, that's why you see that the beam dimension is 500 mm, and then the column dimension is 300 mm for the top end of the column. Bottom end also the same, right? So this one we are using the BS 8110. Okay, so you see that it's condition 1 for the top end of the column, and it's also condition 1 for the bottom end of the column. So I hope you still remember this, huh? All right, so for beta value, let me share the one. So we'll be using this table here. Okay, so okay, so for the top end is considered as condition 1. Because the top end, this one is 500, and then this dimension is 300. Okay, so normally we design the beam as continuous beam. Huh? Okay, so we just take that this top end is a continuous beam with depth of 500, resisting the bending about y-axis with the column dimension of 300. Okay, so 500 is greater than 300. So meaning that the top end is condition 1. Okay, or this is for condition 3 where the beam is simply supported. We should be looking at this one, right? So the top end is condition 1, bottom end is also condition 1, right? Okay, so if the top is condition 1, bottom is condition 1, then beta is 0.75, right? So the clear height of the column, you see that the actual height of the column is 3 meter. Okay, if you look at the y-axis bending, okay, so it will be this beam and this beam resisting y-axis bending. So this one is this beam and this beam with depth of 500. Okay, if you look from this side, okay, then you'll see that this so the actual height is 3 meter. Okay, so from here to here is 3 meter. Okay, you can also measure the actual height from the middle of this beam to the middle of this beam. So this is the same. This is also 3 meter. right? So you can measure from the top of the beam here to the top of the top beam here also. Is also 3 meters, right? And then the clear height of the column is 3 meter minus of 500. Okay.
Hello, sir.
So okay, is everybody following me?
Yeah, I'm not sure if this is my screen, but I cannot see your.
Oh, I shared the wrong slide. Yeah, sorry. This one, okay? So is this beam and this beam will be resisting the y-axis bending, yeah? So meaning that is the 500 mm depth deep beams on the top and the bottom, right? So the clear height is this dimension here. Probably let me explain it again now. Okay, so if you look from this side, okay, then you see the 300 mm over here. Okay, so this is the 300 mm. Okay, so this is a 300 mm dimension over here. 300. Then this is a 500 mm deep beam. So the top and the bottom beam of all 500 mm deep, right? And then the actual height of the column you can measure from here to here. Okay, or you can measure from the mid height of the beam also. So they are the same thing. Okay, they are all 3 meters, right? So the clear height of the column is this value here. So this will be 3 meter minus of 500. Okay. So that's why you have the clear height, okay, with respect to y-axis. So it's better to denote this as Ly, no? Because we are all calculating with respect to y-axis bending. So Ly in this case is 2,500 mm, right? And then the effective length is LOY, okay? So please label this as LOY so that you know that it's only for y-axis bending. So is this factor beta here multiplied by the clear height of the column. So I get 1,875 mm, right? So lambda y, okay, is the effective length of the column over the radius of gyration. So this one, LOY, we have already calculated from here. And then I for the IYY, okay? This one is IYY, right? Okay? Because for every column, there are two axes, the Z and Y axis, right? So now we are calculating for Y axis. So this is IY, right? So you see that IY is the smaller dimension is cubic, and then the larger dimension is normally is BH cube over 12, isn't it? So you see that this H is actually not the larger dimension, okay? Because this is IY, right? If you are calculating IX, then the one that got the cubic is the larger dimension, right? In this case, For IY, the H is the smaller dimension, right? So this is IY, right? IYY. Then the cross-sectional area of the column is B times H. So it will be 400 times 300. So you get 420 times 10 to the power of 3 square millimeter, right? So you just substitute I into here, okay? And then A into here, and then your LOY, 1875 here. So I get 21.7, right? So lambda Y is 21.7. So this is your column slenderness ratio with respect to y-axis, right? With respect to y-axis bending, yeah? And then we use this expression here to calculate the lambda limit, okay? So we do not know the effective creep ratio, so we just use the nominal value of 0.7. And then the reinforcement also, you have not done the design, so you don't know how much steel is provided there also. So B becomes 1.1, right? And then this is for brace column, yeah? Okay. So we assume that this column is with double curvature. So double curvature, the C value is 1.7 or higher, right? So we can just take it as a 1.7 in this case. And then this term, small letter n here, is actually the axial force over the cross-sectional area over the design strength of the column. So you know the axial force, and you know the cross-sectional area of the column, yeah? And then the design strength is just the characteristic strength over partial safety factor. So normally for concrete in compression, the partial safety factor is 1.5. So this design stress of your concrete column is the characteristic strength of 25 over the partial safety factor of 1.5. So in this case, the small letter n is 0.64. So we just calculate the lambda limit using 20 times A times B times C over square root of 0.64, right? So I get 32.7. So this lambda limit is greater than lambda y, right? So if your lambda y is smaller than the lambda limit, then the column is a short column, okay? So in this case, if you just design the column as a short column, and no second order moments will be included. Okay, so any questions so far up to this stage here on how to calculate the slenderness ratio of the column and then calculate the slenderness ratio limit, okay, slenderness limit using this equation here. Okay, any questions so far? Okay, so no question, then we go back to the slides here.
Excuse me, sir.
Yeah,
How do we determine it's a double curvature column?
double curvature, if you have a moment on the top is like this, okay, and then the bottom one, the moment is like this, okay. So if your moment goes that way,
Sorry, sir, we cannot see your building.
or still, let me share. Okay, can you see it now? Okay, so double curvature column is the column that is having moment on top that way, and the bottom moment is the other way, right? So in this case, the moment here will bend this way, and then the bending of the column at the bottom is the other way around. Okay, so this one is considered as Dover curvature column. Okay, Dover curvature is very common in column design. Okay, because if the arrangement of a beam on top and the arrangement of the beam at the bottom is almost similar, then normally you have the top moment going this way and then the bottom moment going that way. Okay, so in this case, your column will bend this way, right? So you have a double curvature. Okay, so in this side is tension, this side is compression, and then at the bottom end, this side is tension, this side is compression. Right? So this is what it means by double curvature, right? When this tutorial question is not mentioned, so we just use the most common type of bending, which is double curvature for the calculation. Okay,
Okay,
is that okay?
thank
you. Yeah. Right. Okay, so let's look at the area of reinforcement. Okay, so the recommended minimum diameter of longitudinal reinforcement in the column is 12 mm. Okay, but in Malaysia we allow the use of 10 mm. Okay, but it's not very advisable to use 10 mm bars because 10 mm bars are very weak to resist the 10 mm bars is very difficult to get very straight steel bars. Okay, you will be having natural curving here and there. Okay, so 12 mm bars are stiffer, so it will be more straight when it comes out from the factory, right? So normally we recommend a minimum diameter of 12 mm. Okay, and then as I mentioned before, minimum is 4 bars in rectangular column, and then 6 bar in the circular column. So please remember this. So later on, when you design column, don't give me 2 number of bars or 3 number of bars. Okay, you must at least have 4 bars at the 4 corners, right? And then the minimum area of longitudinal reinforcement required in the column is given by this expression here, which is given by this EC2 close. Okay, and then you have to check 2 values, this value and this value. 0.002 times the cross-sectional area of the column, or 0.1 times the axial force, NED, over 0.87 and the U strength of the steel, FYK here. Right? So whichever is larger will become the S minimum. Right? If this value is larger than this, okay, then this value will be the minimum reinforcement. Right? If 0.002 AC is larger than this, then 0.002 AC will become the S minimum, right? So this is what it means by this symbol here. Okay, this calculated value must not be less than 0.02 AC, right? And then the maximum area is 4%, right? So meaning that your S maximum over the cross-sectional area of the concrete cannot be more than 0.04, which is 4%, yeah? Okay, but at laps, okay, 8% is permitted. So at lapping over here, this zone here, you have the lower column reinforcement lapping with the upper column reinforcement. Okay, So this lapping area we allow up to 8%. Okay. And then the next thing is the diameter of link should not be less than 6 mm or 1/4 of the largest longitudinal bar. We mentioned about largest longitudinal bar because sometimes we use mixed bar size. Let's say, for example, sometime for a cross section, we use a larger bar size at the corner and then smaller bar near the middle of the column. So this bar size may be different from this bar size. So in that case, you must use this as the largest bar size here. This one, this bar size. So the largest longitudinal bar. And then the maximum spacing of links in column should not exceed. So this one is from this close, EC2 close 9.5.3. So it should not be more than 20 times the minimum diameter of the smallest longitudinal bars. Okay, so probably you just cross out the minimum, no? Okay, so it must be 20 times the diameter of the smallest longitudinal bar. Okay, this one is double of this one is double of what I'm describing. So just cross out the minimum, right? We just have to mention that it's 20 times the diameter of the smallest longitudinal bar. As I mentioned here just now, we have larger diameter bar and then smaller diameter bar over there. Okay, so smaller diameter bar should be used in this calculation of 20 times. Okay, and then the least lateral dimension of the column, right? So just now we have, in the example, we have a column 400 by 300. So we must use the 300 mm as this, the least lateral dimension of the column, right? And then the last one is 400 mm, which is a fixed number. Okay, so you have to calculate these two, you have to calculate these and then use the least dimension of the column and then 400 mm. So let's say from here you calculated is 250. Okay, and then the least dimension of the column is 300. Okay, so this 400 is fixed. So the maximum spacing of the links should not exceed this one. Okay, if you use 400, then they exit 250. Okay, so cannot. If you use 300 also, you exit 250 already. Okay, so this 250 will be the governing link spacing, right? And then within the distance equal to the larger dimension of the column above or below a beam or slab and near lap joints, this spacing should be reduced by a factor of 0.6. Okay, so what it means here is okay, so let's say this column here is 400 by 600, no? Sorry, 400 by 300. Okay, so this link here, within this distance of the larger dimension, okay, so meaning that within this 400 mm here, your link spacing must be smaller, okay? So normally it's 0.6 times of this one, bottom also the same. So this one is 400 mm. This one is also 400 mm. Okay, so within this region here, you must have a link spacing of only 0.6 times of what you have here. Okay, so this is what it means by that expression. Okay, reduce by a factor of 0.6. So this is where the column top end and the bottom end, you should have only 0.6 times of this value here. Okay, so meaning that at this region, your spacing should be only 150 mm or less, right? Here you can, near the middle here, you can provide spacing of 250, but near the end of the column, at a distance of the larger dimension of the column, you have to provide links which is nearer to each other, which is 0.6 times of 250. So that gives you 150. Okay, so we'll look at these all details here when we go through the examples, right? And then every longitudinal bar, this should be bar, every longitudinal bar or bundle of bars placed in the corner should be held by transverse reinforcement. So no bar within the compression zone should be further than 150 from a restraint bar, right? So if we have a beam, also not beam, column cross section like this, okay? So if you have a bars arrangement like this, okay? So meaning that you have to provide links that must enclose the corner bars, right? All the corner bars must be restrained by a link, right? And then no bar within the compression zone should be further than 150 mm from a restraint bar. Right? Let's say you need reinforcement in this column like this, 9 bars. So all these corner bars, you should provide full links that restrain that is tied to the bar. Okay. And then this bar also tied to this links here. So this bar also tied to this link here. So you have one unrestrained bar. So no link is restraining this column reinforcement. Okay. So if this distance is, if the distance of this bar from a restraint bar is more than 150%, 150 mm, then it's not allowed, right? If this bar has no links tying it up, right, then it becomes an unrestrained bar, right? So you have to measure the distance from, use a different color, okay? So if this distance is more than 150, okay, then you need to provide a link which will go through this beam also and this bar also. Okay, so your link may be, so probably you need to adjust your link so that you go through all the bars. So probably you provide a link like this. and then another link like this. Okay, so that all the bars are restrained by the links, right? If this distance is more than 150 mm, right? So meaning that this distance here is more than 150 mm, okay, measured from center to center, right? So this is what it means by this statement here. No bar within the compression zone should be further than 150 mm from a restraint bar. So in this case, we restrain all the bars because if you provide a link like this, then this bar become unrestrained. Okay? If it's allowed, if this distance is less than 150, if it's more than 150, then you have to use the red color link. Okay? If this distance is less than 150, then you can use the green color link. Okay? With the link not going through the bar here, unrestrained bar. Okay, so this is what it means by this statement here. Right? Right. Next, we move on to the short column resisting axial force and moments. So here we say that axial load and moments of the column may be obtained using the subframe analysis. Okay, and then the area of longitudinal steel of this column is designed by. There are three methods, right? Okay, so we will only be using this method here. Okay, using the design charts, right? And then these design charts are actually plotted using the basic design equations, right? So instead of using a solution of the basic design equation, we just use the design charts, right? That is developed from the solution of basic design equation, right? So this one you only learn in master's course, if you want to solve the basic design equation, right? And then the third method is the approximate method, which you will not learn. Okay, so whichever design method is used, EC2 requires that geometric imperfections in the structure should be taken into account. So this is what it means by imperfection moments, right? Because in actual construction, you will not be having a perfect column where the load is axial load is exactly at the center of the column. Okay, so the beam here and the beam here may be the beam connected to that column also may not have perfect dimension also. Okay, so due to all these construction errors, you will have a moment that will be transferred to the column due to the imperfection of the construction, right? Because the beam that you design to 300 by 500, probably you go to the site and measure, you get 295 by 503 mm. Okay, so this is what we call as imperfection, right? So due to those imperfection in construction, there will be imperfection moments. Okay. So in the case of a single column, we assume that the geometric imperfection will result in the column being slightly out of plumb, such that the axial force acting at each end of a column will be eccentric to the other end by an amount taken as L0, which is the effective length. So if you are considering y-axis, then it's L0y. If you are considering z-axis, then it's L0z over a constant 400. Okay, so this will result in an additional design moment of the axial load times the eccentricity of LO over 400. Okay, If you have y-axis, then you use LOY. If you're using calculating for z-axis, then use LOZ, right? So we have all this in the design equation letter, yeah? Design examples, right? And then furthermore, a column should not be designed for a moment less than the axial force times the minimum eccentricity, right? So minimum eccentricity is h over 30 or 20 mm, whichever is larger. Huh? If your h over 30 is less than 20, then use 20 mm. If your h over 30 is larger than 20 mm, then use the actual h over 30 value, right? So as I mentioned here, in design equation, h is not always the larger dimension, right? H depends on the axis of bending. Okay, so here you have a Z axis and then Y axis like this, right? Okay, if you are calculating for Y axis, okay, then you should be using this dimension as H, which is perpendicular to the axis of bending. So always remember, H is the dimension perpendicular to the axis of bending, right? If you are considering major axis bending, major axis is Z, then H will be this dimension. Okay, so in this case, H will be the larger dimension, right? But if you have Y-axis bending, then H will be the smaller dimension over here, right? So be aware of that. Huh? So always remember which axis of bending are you calculating. Then you use the proper H value, right? Okay, so the design charts are plotted using all these basic bending theory that you have learned in the beam. In beam design, have everybody seen this diagram? The
Yes.
cross section, the strain distribution, and then the compression block here, right? Because beam, you have only bending moment, right? So this strain here is only caused by bending for beam, right? But for column, you have compression, okay? So because of that compression, okay, then most part of your cross section will be in compression, right? If you look at beams that you have learned, you look at beam, the neutral axis is actually much higher, right? For beams, right? But for column, the neutral axis is much lower, okay? Because of the axial load that is acting into the page here, okay? So this one is the cross section of the column, and then the axial force is actually acting into the page, right? So it will cause more compression in the cross-sectional area of the column. So it's slightly different from beam. Normally beam, the neutral axis is very high over here. And then the compression block is also quite shallow, right? But in column, the compression block is much lower, right? So these are all the basic theory, okay, that we use to calculate all the values in the design charts. Okay, so if you want to solve the design equation, this one refers to solution of the basic design equations, right? You can calculate the force equilibrium using all these forces here, okay, for the solution of the basic design equations, right? But in our course, we were only using the design charts based on this solution of the basic equations, right? Right, so these are the basic equations that we can write based on the force equilibrium and also the moment equilibrium, right? But we're not going to solve these basic equations, okay? We will only use the design charts that are based on these basic design equations, which looks like this. So all this has been used to plot the charts like this, right? Okay, so this chart we have NED over BH FCK. So we only need to know this term here and then this term here. MED over BH square FCK, right? And then this value of V and H depending on the axis of bending, as I mentioned just now. So H is not always the larger dimension, okay? If you are calculating for y-axis, normally H is the smaller dimension, right? If you are calculating for z-axis bending, then normally the H will be the larger dimension, right? So be careful of all these, as I explained just now. Okay, you have Z. This one should be y-axis, and then this one should be z-axis, right? If you are considering z-axis bending, then your H is this dimension. Okay, so if you are considering y and axis y bending, then your H is this dimension here, right? Okay, so I hope you understand all these, right? So now let us look at another tutorial question here. So we have a building frame like this, right? And then is a heavily loaded industrial structure where the center of column of line PQ below the first floor is to be designed. Okay, so we will be designing this column here. Okay, so if you want to design this column, then we have to make sure that our arrangement of load is giving this column the maximum as axial load and also the maximum moment, right? Right, so the permanent action including self-weights of the beams and slab is 10 kilonewton per square meter, right? The variable action is 15 kilonewton per square meter. Okay, so all these actions are on plan. Okay, so on the plan of the building, you have this GK equals to 10 kilonewton per square meter. And then variable action is 15 kilonewton per square meter. And then concrete strength is 25 Newton per square millimeter. And then the yield strength of the steel is 500 Newton per square millimeter. So take the column self-weight as 14 kilometer. Okay. So meaning that this column is 14 kilonewton. This column is also considered as 14 kilonewton, right? And then the effective height of the ground floor column has been estimated to be 2.34 meter. So if the effective length or effective height is already calculated, okay, then meaning that this is the, you can calculate the lambda already using this LO. Okay. And then for the first and second floor, okay, the effective length is 1.8 meter. So in this example here, we will ignore geometric imperfections. Okay, just now in Eurocode, okay, it says that we must take in imperfection moment. So in this particular example, we said that we ignore imperfection moments, so meaning that we don't need to calculate these imperfection moments, right? Right, so we ignore this one. Okay. So this is the solution. So here is the loading calculation. So maximum ultimate load at each floor. Okay. Before that, let's look at the arrangement of load first. So in order to get the maximum axial load on this column, okay, so we put maximum load on the first floor and we put maximum load on the roof floor also. Okay, because we are not calculating the moment in these two columns. We want the maximum moment in this column, right? And then we want the maximum axial load transferred to this column. So here, if we put all maximum on the roof and the all maximum on the first floor here, it will transfer the maximum axial load to this column, right? But on the first floor here, we cannot put maximum load here because we want to transfer the maximum moment to this column. So if we want maximum moment to this column, then we should put the maximum load on the longer span and then the minimum load on the shorter span, right? So that's why the loadings for the design of this column here looks like this, right? All right. So now I want to look at the loading of how much is GK here and how much is QK there. Okay. So the maximum ultimate load at each floor, okay. So per meter length of the beam, right, is 1.35 times GK plus 1.5 times QK, right? So where does this 4 come from, right? So this 4 come from here. Okay, because this is 4 meter. Okay, if our column is here, right? So this is a plan view already. Okay, you look at the plan view. So this is the column of concern, and then if you continue on this side here, you still have a 4 meter length plan. So there's another set of beam here, another column there, and then another set of beam there, and then another beam connected to another column there, right? So to transfer this load to this column P here, okay, column PQ, right? Then the load that is going to be transferred to that column PQ here is actually all this area, okay? This area over here, okay? So this is the middle. So this is 2 meter. This is also 2 meter. So meaning that this area that is going to be transferred, the load to the column P is 4 meter. So that's why you have the 4 meter here. Okay, understand all this? Does everyone understand what I'm explaining here? Okay, so the total load that is going to be transferred to this column, okay, is the one that is the shaded area here. So all this load will be transferred to this column, okay? But normally the load will be transferred to the beam first, and then the beam will transfer the load to the column, okay? Okay, so that's why we have the 4 there, right? And that is per meter length of beam. Okay, we only multiply the load by the width to get the load per meter length on the beam. So I hope you understand what is going on here. Okay, let me explain another time. Right, so just now we said that the total area that is going to be transferred, the load is 4 meter width. Okay, so this is 4 meter. All right. Okay, so first we calculate how this load is going to be transferred to the beam. All right, so this load here and this load here will transfer the load to this beam here. Clear? This beam, okay, and then let me say that this is the blue color area. Let me draw again. Okay, so this load and this load will be transferred to this beam. Okay, and then this load and this load will be transferred to this beam. Right? Okay, so now we want to calculate what is the load that is transferred to the blue beam there. Okay, this blue beam, right? So that will be this total load on this area here, right? Okay, so this is a 6 meter. So you just use the load, the area load here. So GK is 10 kilonewton per square meter. Okay, so the total GK that is going to be transferred to this beam here, okay, is 10 times this area, right? Correct? That will give you the total load. Okay, so this area is 6 times 4 meter, right? So this is 6 meter, this is 4 meter, right? Okay, so I multiply by the GK. So this is the area load, multiply by the area, you get the total load, right? But we don't want the total load. We want to know what is the load per meter length on the beam. So we divide by 6 again, right? So this 6 and 6 will be cancelled off. So you have only 10 times 4 meter, right? This is kilonewton per square meter, right? So this one is meter, and then this is per meter. So I'm going to get 40 kilonewton per meter length on the beam, right? If you calculate for the red color one, okay, it's also the same thing, okay? So the GK transferred to this beam here is 4 meter in this direction times 4 meter in this direction to get the area. So it will be 4 times 4 and then multiply by the area load of 10. But this is the total load. We want to know what is the area load, the load per meter length transferred to this beam. So we divide by the span again. So 4 cancel off. So it becomes 10 times 4, which is also 40 kilonewton per meter length. So in effect, it's the same thing. Okay. So you don't calculate for, you don't have to calculate for 2 times. Okay. We just say that the load per meter length on the beam will be just the area load multiplied by the width of 4 meter. As you can see here, isn't it? 4 by 10, and then this is also 4 by 10, right? So this is how we get the 4, okay? And then multiply by 10. Okay, so it is 4 by 10, but don't forget the partial static factor of the load. So 4 times 10 times 1.35. Okay, will be the total dead load that is going to be transferred to the beam as load per meter length. And then for the QK, also the same thing. Okay, for the live load, also the same thing. Okay, still the same area. It's just that QK is 15 kilonewton per meter length. So this one becomes 15. This one becomes 15. Okay, so it's not more 40, right? This one is 60 already. Okay. So therefore you have 4 times 15, which is 60, and then multiply by the partial static factor again, you get 144 kilonewton per meter length, okay, for W max, right? Because W max is 1.3 times GK plus 1.5 times QK, and then multiply by the width of the flow, area that is going to transfer the load to the beam, okay? So we do not multiply it by the length of the beam, as I mentioned just now. We are not interested in that total load. Okay, we are not interested in this total load. We are not interested in the total load, but we're only interested in the area load multiplied by the width of 4 meters, right? So is everybody following me? Is everybody okay with that? Any questions so far on calculation of the load? Okay. And then minimum load calculation is also the same, but minimum load, you have only 1.35 times GK, right? Then we just multiply by the width of the flow that is transferring the load to the beam. Then we get 54 kilonewton per meter length. Okay, so this is the maximum load on the beam. This is the minimum load on the beam per meter length, right? Okay, so once we know how much of W max and W min, then we can calculate the total load that is transferred to the column. Okay, so the load that is transferred to this column here are from the loading on this floor plus the loading on this floor plus this column load plus this column self-weight. Okay, this column self-weight, this column self-weight. Okay, so for the load transfer, this strictly speaking is a continuous beam. Okay, but for the load transfer, we can assume that this beam is simply supported. This beam is also simply supported. So meaning that the reactions of this beam is symmetrical. So half of the load will be transferred here, half of the load will be transferred here. Same as for this 4-meter beam. Half of the load will be transferred here, half of the load will be transferred here. So that's why you can see that the column, this column load here will be this load, the load that is transferred from this beam to this column, plus the load from this beam that is transferred over here. Okay, so let's look at how much load is transferred here. So the load that is transferred here will be W max times 6 over 2, isn't it? 144 times 6 over 2. So that will be the load of this load transferred to this column here. Okay, and then we have also this beam transferring half of this load to this column here. So this one is also W max, right? So you have 144 times the length of 4 divided by 2. So half transferred here, half transferred there. Okay, so the total load that is transferred to this column here is this, right? Okay, the half of the load from this beam here and then half the load from this beam here. Okay, 144 times 6, which is the length, and then divided by 2, that will be the half of this load. Yeah? And then 144 by 4 over 2 will be half of this load here. Okay, from this flow. Okay, and then this flow also the same. But this second flow is the same as the top flow here. That's why we multiply by 2, right? So this 2 times of this whole thing will be the load transferred from this flow plus this flow, right? Okay, so this load will be transferred here, and then you go down from this column, and then plus this load, and then go down this column, and then transfer to this column, right? So this load is from this flow, and this flow. Okay, and then from this flow, the arrangement of load is a bit different because you have W max here and then W min here. Okay, so the load that is transferred from this one is 144 times 6 over 2, same as this and this also because it's the same load. Okay, but for this load is different, right? This one becomes 54 times 4 over 2. Okay, so that is the first flow load transfer to this column. Okay, and then again we have this self-weight of column transferred to this column also because this column has to support these 2 column weight also. So this one column will say that we assume as 14 kilonewton. So this column has to resist the self-weight of 2 columns above it. So you have 2 times 14, right? So you add all this up from the second floor and third floor, and then from the first floor, and then from the column self-weight, then we get 2008 kilonewton as the axial load that is transferred to this column here. So is everybody following me? Is everyone okay? Or any question on the calculation of this load here? Okay, no question. Then we move on to calculate the what you call the column moment. Okay. So this one we use the BS810 subframe division. Okay. So we want to design this column, so we have to take this column and then the column above it, and then the beam connected to this column, and then fix all the other ends, right? So we fix this, fix this, fix this, fix this, and then this one is maximum load, and then this one is minimum load, okay? And then this beam stiffness have to divide it by 2, okay? And then this the column. Okay, so this column is 3 meter. This column is also 3 meter, right? So 3 meter, 3 meter, we use the length of the column to create the subframe. Okay, so this is 3 meter, this is also 3 meters, right? So this beam, okay, the B is 300 mm and then the H is 700 mm, right? Okay. Okay, so now we are considering bending about this axis here. This axis, huh? Okay, so that's why these beams will be restraining the bending about this axis, huh? Okay, so this beam is 300 by 700, okay? So meaning that B is 300 and then the depth is 700 for the beam, right? So this is BH square over LBC. This is BH square over LAB. So length of AB is 6 meter. BC is 4 meters. Huh? So this is 4 meter. This is 6 meters, right? And then we take only half of the stiffness, right? This is BC also, half of the stiffness only. Column, the cross section is 0.4 times 0.3. Okay, so now we are designing for the calculating for the major axis, right? Okay, so the column, if we look on plan, right? This is 400 mm, okay, and then this is 300 mm. So we're actually calculating about z-axis bending, isn't it? Okay, so z-axis bending, the H is 400 mm, right? Okay, so all these are about major axis bending, yeah? Okay, then after that, we just calculate the total stiffness. So column, we have 2 columns. So 2 times 0.53. And then for KBC is half of KBC, which is 1.07. And then for KAB is half of KAB here, so it's 0.71. So this is the total stiffness. So meaning that the distribution factor for the column moment distribution is 0.19. Okay, and then these are the fixed end moment. Okay, we have a clockwise moment from AB on this side, and then we have an anti-clockwise moment from BC on this side. Okay, so we have minus 432 plus 72, right? Okay, so 432, this is supposed to be minus 432 for this one. Okay, and then this is plus 72 for this side, right? Okay. You can use minus 432 plus 72. You get negative 68.4 kilonewton. But here I'm only calculating the magnitude. Okay. So I only need to know what is the magnitude of the moment, right? But for you, you can make use of the sign of minus 432 plus 72 over here. Okay, if you want to know what is the direction of the moment. But here I'm only calculating the magnitude. Okay, so meaning that this is not giving you the correct direction. Okay, so this is only giving you the magnitude. So this is z-axis bending, so it's mz, right? And then, as I mentioned just now, we need to calculate the minimum moment, right? We do not need to calculate imperfection moments because the instruction says ignore imperfections. But minimum moment is compulsory. Okay, so minimum moment is based on h over 30, the eccentricity of h over 30. So we are calculating for z-axis bending, then h is the larger dimension, right? But this one only 13 mm, so we have to use 20 mm as the eccentricity. So the axial load times the eccentricity will give you 40.2 kilonewton meter. So this is less than the one that we calculate from the subframe analysis. So meaning that this is the governing design moment. So your design moment is 68.4 kilonewton meter. Okay. So now we know the axial force already, the design axial force, and then the design bending moment. Okay. And then we assume that this is a short column, right? Or is it mentioned in the question already? So this is the, so it's not mentioned anywhere whether the column is short. I think I forgot to put in the description saying that this is a short column. Okay. Or do we have the calculation later on to show that it's a short column? It's not mentioned anywhere, but take it as a short column in this case, right? Right. So if in order to use the design chart, okay, we need to calculate this term where it is NED or BHFCK. So what I mentioned here, we have to be very careful about this H value here. Okay. If it's about major axis, then H is the larger dimension. If it's about the minor axis Y or Y axis, then H will be the smaller dimension. Right? So in this case, we are calculating for Z-axis bending. So H is the larger dimension of 400, right? This one, it doesn't affect the M value, but this one, it affects this value here. Because if you use the wrong dimension to put as a square here, then this is wrong, right? So be careful about the axis of bending. Yeah. So for major axis bending, H is the larger dimension of the column, right? And then there's another term of D2 over H. So D2, I have to open up the design guidebook. Yeah. So you see all these design charts here, they all have the D2 over H value. Okay. So how do we calculate D2 over H? So D2 is actually the depth of the bar. Yeah? Okay. Okay. So this D2 over H is actually from the depth of the bars, right? Okay, you have reinforcement like this, right? And then if this is the axis of bending, okay, then D2 is measured along the H value. So if this is z-axis, okay, then this one becomes the H, okay, and then this is D2. So D2, you have to take it as the same direction of H, okay. If your H is this way for minor axis bending, then your D2 should be this dimension. Okay, so D2 normally is the cover plus, because you have links, okay, so normally it's the cover, concrete cover plus link diameter plus half of the steel diameter, right? Okay, so we assume that is 80, right? And then 80 over 400, I get 0.2, right? Then if I have 0.2, then I have to refer to the D over H diagram of D of 2 over H of 0.2. So don't use the wrong charts. Okay? You always need to calculate the D2 over H value, right? Okay? So this D2, as I mentioned just now, normally is the cover plus the link diameter plus half of the steel diameter. Okay, longitudinal steel diameter. But in this case, I did not calculate, I just assume that it's 80. Yeah? Okay, if you need to calculate based on the cover plus the diameter, then you need to calculate that. Right? So now I know D2 of H is 0.2. So I refer to the 0.2 chart, right? And then based on NED over BHFCK of 0.7 is somewhere here. So this side is NED over BHFCK. Yeah? So this is 0.6, this is 0.7, so 0.67 is roughly here. And then for MED over BH square FCK, we have 0.057. So you have 0.05 here, and then 0.06 here. So 0.057 is somewhere over here. So you just go up here, and then from here 0.67, and then from here 0.057. Then you hit a point here. So this point is between 0.3 and 0.4, isn't it? Okay, so this 0.3 and 0.4 values are the ASFY over BHFCK, right? So meaning that from 0.3 to 0.4, you still have another, imagine that you still have another, from 0.3 to 0.4, you have 10 lines there. Okay, you have 10 lines in between. So this point here referring to the line of 0.31, right? or 0.32, right? Okay, it's nearer to 0.3, okay, it's far from 0.4. So you just estimate what is the decimal points, right, for here. You can probably, from my estimation, is 0.31. Okay, maybe you said it's 0.32. So that depends on your own estimation using your own eyes. Okay, so this 0.31 is actually this value, ASFYK over BHFCK. Okay, so I just bring the FYK on the other side. Okay, then I can calculate what is my AS. This AS required is actually from this expression here. Okay, so my AS FYK over BHFCK is 0.31. So this becomes my AS required. Okay, you just bring all these terms on this side and FYK on the other side. Then I get AS required of 1,860 square millimeter. Okay, so this is my AS required. Right? Then I calculate my minimum reinforcement using this expression. So I know my axial force. I also know my design strength, not design strength, this is use strength of the steel. So this one is 462. And then if you calculate using 0.002 AC, AC is just B times H, the cross-sectional area of the column. So it's 240. So 462 is greater than 240. So meaning that the minimum steel area is based on this 462. Okay. And then the maximum is 4% of the cross-sectional area BH. So 4,800 square mm. And then at lapping, it can be doubled. So 9,600 mm, right? Square. So based on minimum, maximum, and required is between maximum and minimum. So we're able to provide steel area based on 1860. Okay. So let's say we use 25 mm bars. So 25 mm bars, 4 bars will give you 1964, right? Square millimeter. So 4 bars gives you 1964 square millimeter. So I just provide 4H25, right? And then for the links, we said that it cannot be smaller than 1/4 of the larger diameter. So we only use one diameter size, so only the larger or the smaller diameter is 0.25. Okay, so I get 6.25. So this is greater than 6 mm. So we need to provide more than 6 mm. Right? If this is less than 6 mm, then you can use the 6 mm bars. 6 mm bars for links is the smallest. Okay, and then maximum spacing of link is 20 times the smaller diameter. So we only have one single diameter, so the smaller diameter is also 25. Larger diameter is also 25, right? So this is 500. And then the least dimension of the column is 300 mm. And then we have another requirement, which is 400 mm. So based on this 500, 300, and 400, we have to use the 300 mm because it must be the smallest of these three values. Okay, so the maximum spacing is 300. You cannot use 500 because 500 is more than 300. You also cannot use 400 because 400 is higher than 300. So we must use only 300 mm for the spacing. So from here, your bar diameter cannot be smaller than 6.25 mm. So the next larger bar will be 8 mm. So we use H8 and then a spacing of 300. Okay, and then for this end and this end, we say that the link spacing can have to reduce to 0.6 times of this normal maximum spacing for 180 mm for at least 400 mm above and below this column. this 400 comes from the column dimension. Okay, so this 400 is the larger dimension of the column. So meaning that within this 400 mm, you have to provide spacing not more than 180 mm. Okay, and then the rest of the column, you can provide the spacing of 300 mm, right? So why do I not using 180 here? Okay, because normally for link spacing, we use a multiple of 25 mm. Okay, multiple of 25 mm, meaning that is the value that can be divided by 25, and then you get a non-decimal, you get a round number. Okay, so 175 is 5 mm smaller than 180, so it's allowable. Okay, so how do I get this 525 mm here? This one cannot be exactly 400. Okay, it must be 400 or more, right? 400 for at least 400 mm. Okay, so 175. So the distance to the next link is 2 times of 175. So it's still less than 400. Okay, we only have 350. And then you put another 175 there, then we get 525. 525 will be more than 400, so it's okay, right? So meaning that you have 3 equal spacings. So meaning that from here to here, you have 4 links. Okay, we have 3 spacings, which is 3 times 175, you get 525 mm. Okay, the bottom also same thing. Okay, this must be at least 400. Okay, if you provide only 3 links, then it's only 350. Then you provide 4 links with distance of 175, then it becomes 525, right? And then the cross section of the column will look like this. So the 400 mm will be the H. So this is the axis of bending, ZZ axis. So the bars must be provided at 4 corners. Since we have only 4 bars, then we have only bars at the 4 corners. And then we have a link going through all the bars like this with closed links. Okay, so this link will be having spacing of 300 on this region of the column, and they will be having spacing of 175 near the bottom end and near the top end with at least 400 mm. 400 mm is the largest dimension of the column. So this must be more than 400 mm or more than the larger dimension of the column. Okay, so that is the design example. So any questions so far? Okay, I hope you can follow my lecture for today, because online is not so effective. Okay, because my illustration have to depend on I don't have a tablet over here, so I have to use my mouse to draw all the drawings, which is not so nice, but I hope you understand, okay, of all my illustration there. So any questions so far? Okay, if not, I will just end my lecture today here. Okay, I have to go very fast and overshoot a little bit because we are missing quite a lot of lectures, right? So I hope I can still catch up with the lost lecture there, right? Okay, so I'll see you again after Hari Raya. Okay, so our next lecture will be on the 15th of April, right?